This is a tutorial video on celestial coordinates, specifically the local coordinates of altitude and azimuth, as well as the celestial coordinates or the equatorial coordinates of right ascension and declination. What we should really call celestial latitude and longitude, but astronomers call them right ascension and declination. I'm going to be going over these coordinate systems in the program Stellarium, so this is also a bit of an introduction on some of the features of the planetarium program Stellarium. All right, so first of all, let's talk about those local coordinates, altitude and azimuth. Altitude is just the angle that something makes in the sky relative to the horizon. Altitude sounds like something you would measure on in a plane altimeter, and it would have units of meters. It would be the height above the ground or the sea level. That's not what astronomers mean when they say altitude. It's an angle, so it's going to be measured in degrees. We could measure it in radians or some other unit, but degrees. Degrees, arc minutes, arc seconds, and it's the angle that the object makes with the horizon. So there you see the sun kind of over in the east, and if I actually click on it, Stellarium will give me information about its altitude and azimuth. By default, it actually gives you a lot more information, but one of the things I've done here, if you go into the configuration window for Stellarium, you can control how much information you see when you click on an object. So if I click on that or hit F2 key, and if I go to this information tab right here, then selected object information, I just want to see the name and its altitude and azimuth for right now. So you see the altitude of the sun is 47 degrees, 59 arc minutes, and some arc seconds. And when this turns over to 0, the next degree marker goes up, so it's at 48 degrees above the horizon right there. Now, the horizon has an altitude of 0, so when an object is rising or setting, its altitude is 0. And then the highest altitude you can have is directly overhead. That's what astronomers call the zenith, or zenith, and that's an altitude of plus 90 degrees. You could have negative altitude, which would mean the object is below the horizon, so you normally wouldn't be able to see it. And that's perfectly fine. And then at negative 90 degrees would be what we call the nadir, N-A-D-I-R, which is opposite the zenith. So the reference plane for this local coordinate system of altitude and azimuth is the horizon. The other angle is the azimuth, and azimuth is just where along the horizon is the point directly below or above. Below if the object has a positive altitude, so it's above the horizon, and then the point that would be above an object that was negative altitude below the horizon. So you drop down to the point on the horizon below where that object is, like there's the sun right there. I just drop straight down, and then that intersects the horizon somewhere, and now I can measure its azimuth. Azimuth is really just a compass heading, compass bearing around the horizon from the reference point, which is due north. So due north is 0 degrees azimuth, due east is 90 degrees azimuth, due south is 180 degrees azimuth, and then due west is 270 degrees azimuth. And then when you get around to north again, it resets to 360. So you get 358, 359, 0 degrees azimuth. So if we look back here at the sun, there's the sun right there. I drop straight down. It's now 48 degrees above the horizon right there. And its azimuth should be a little bit more than 90 degrees because it's a little bit south of due east. And you see its azimuth is 101 degrees right there. I actually have a plugin in Stellarium that lets me show the compass marks. So if I turn that on, you can see, oh yeah, there are the azimuth angles from 0 to the north, 90 to the east, 180 to the south, and so forth. So that's altitude and azimuth. It's kind of like the coordinates you might put into a cannon if you were going to aim it somewhere. You'd say, okay, elevation or altitude 45 degrees above the horizon. You turn a big crank and the gun goes up to steeper angle. And you say heading 165 degrees, and then you turn another crank and it turns and points in that direction. And so those are the local coordinates. There's an important reference line for the local system, which is called the Local Meridian. That is a line which goes from due south directly overhead through the zenith, and then down to due north and intersects the horizon due north. So let me turn that on. If I go over here to Sky and Viewing Options window, or hit the F4 key, one of the options is markings, and you see here celestial sphere. I can draw a meridian line. So now there's a line right there, kind of greenish, that goes from 180 through the zenith up there. And then if I turn around to the north, it goes into the north horizon. Now, technically, there's an upper meridian and a lower meridian, but for most purposes, it doesn't matter. You can just think of the meridian as going from south to overhead to north, and that's what's important. Now, the meridian is a useful reference line because everything that rises and sets through the sky has to cross the meridian at some point. If I speed time up, you can see that there's the sun going across the sky from east to west. At some point, the sun sets over there, and the Earth is spinning way too fast. There goes the sun again across the sky. You see I still am showing its altitude and azimuth. There it's negative, it's below the horizon. There, when it's positive, it's above the horizon. You see the altitude is increasing until it gets to 360, and then it flips around to 0. That's true for all the stars as well. Let me slow this down a little bit here. All right, so there's the sun crossing the meridian. That's going to be local solar noon. That's when it's going to be at its highest possible altitude. And of course, its azimuth has to be exactly 180 degrees because the meridian, everything on the meridian has an azimuth of 180 degrees if it's south of the zenith, or 0 degrees if it's north of the zenith. Let's see, when the sun goes down again, we'll look at a couple of different stars. So let's watch the sun go down. The sun's setting north of due west because it's summertime. And there are the planets that are out tonight, and then here are some bright stars. Let me just bring the playback back to normal speed here. And there's the star Vega right there. Now, Vega, you can see, has an azimuth of 75 degrees, so it's kind of basically east, a little bit north of east at that point in time, right? There's 90 degrees is due east. Let me go back to the direction markers like so. So there's due east right there, and its altitude's pretty high. It's at 50 degrees and 29 arc minutes. And as time passes, its altitude gets higher and higher. And if I speed time up again, speed time up by 10, 100, 1,000, we can watch its altitude get higher and higher until it crosses the meridian. So here at some point, we'll pause when I get close. All right about there. I didn't get it exactly, but I'm close. It's at azimuth 176 and 54 arc minutes increasing. And there you see its altitude 87 degrees and 29 arc minutes. Oh, it's very close to 90 degrees. At this particular latitude in New Haven, Vega almost passes through the zenith, but not quite exactly right. Not quite exactly. So it's still going up very gradually because I'm not quite at the meridian. Once it crosses the meridian, this number is going to stop going up and start going down. So astronomers generally want to observe an object when it's as close to the meridian as possible because we want to observe objects when they're at their highest possible altitude. That is because when they're at the high altitude, you're looking through less atmosphere. If we look at an object that's down here at low altitude, close to the horizon, we're looking through maybe 2 or 3 times as much atmosphere as when we look overhead. And the atmosphere has the effect of dimming objects. That's why the sun is so much dimmer when it's rising or setting. It also will redden objects, so just like the sun looks very red at sunrise and sunset, because the atmosphere is preferentially scattering blue light. So the sun is the light from the sun is being scattered to make the sky blue somewhere west of you when you see a nice red sunset. The other effect that the atmosphere has is that the turbulence in the atmosphere will cause the stars to twinkle or shimmer, if you like, and that will blur out your view of the universe when you're looking through extra atmosphere. I mean, you'd love to have unlimited time on the Hubble Space Telescope so you can not look through any atmosphere, but here with a ground-based telescope, you have to minimize the atmosphere you look through, so you want to look when it's as high in the sky as possible, the highest possible altitude. Now you can see Vega's crossed the meridian, so the altitude here is slowly decreasing. So let me just, to review that, turn on the altitude and azimuth grid. So if I go down here, if I were to hit the Z key, Stellarium turns on this altitude and azimuth grid. So you can see these wedges that are coming up and converging at the zenith. Those are wedges of particular azimuth, constant azimuth. And then these circles that go up from the horizon to the zenith, those are circles of constant altitude. So that's 10 degrees right there, 20 degrees, 30 degrees, and so forth, all the way up to 90 degrees. And then you can see the same with the azimuth markings here. As the Earth turns, the stars will change their altitude and azimuth as they rise in the east, cross the meridian, reach a maximum altitude, and then start setting in the west. I have a nice kind of simulation of this as seen from outside the celestial sphere, outside the dome of the sky. Now, this is, of course, an impossible thing to do, but this is kind of a convenient model to have. This is based on the University of Nebraska astronomy simulations. You can go to this website to see the animations and simulations that they made for their astronomy classes at University of Nebraska, and they put these online. They're very useful for teaching intro astronomy. Anyway, this one is the Azimuth Altitude Demonstrator, and you see a little stick figure there in the middle of his horizon, and you can see north, south, east, west marked on the horizon. You can always figure these out because by definition the direction the Earth turns is east. So this must be the direction the Earth has to turn, and then 90 degrees to the left of that is north, 90 degrees to the right of that is south, and so forth. So you can see those reference points. You can see the meridian right here going from south to overhead to north. There's the zenith, there's the nadir, and you can just see the altitude 45 degrees, up to close to 90 degrees, down to 10 degrees or less. They can be negative if it's below the horizon. And then you can also see the changing azimuth right here, right? So if I drag the star around to the north, the azimuth decreases like so. And if I drag it back around to the south, the azimuth increases. If it were exactly on the meridian, its azimuth would be exactly 180 degrees. And so I can specify any point in the sky by using these two angles, with 0 altitude at the horizon and 0 azimuth at the north horizon, due north on the north horizon. If I were to go to 0 azimuth and 0 altitude, that should be exactly on the north horizon. Dial that in. Let's put 0 in here, in fact. There we go. So there's that. A star that were at that point would be at 0 altitude and 0 azimuth. All right. Well, let's move on to talk about celestial latitude and longitude. This is a coordinate system which doesn't actually depend on your local horizon. This is a system that's based on the celestial equator and the celestial north and south pole, as well as the ecliptic, the path the sun takes in the sky. So celestial latitude and longitude, or in astronomy we call them declination for celestial latitude and right ascension for celestial longitude. They're defined very much in analogy with terrestrial latitude and longitude. So every point on the surface of the Earth has a particular latitude and longitude. And the latitude is measured from the equator around the curvature of the Earth. So the equator would be 0 latitude. The North Pole would be plus 90 degrees north, or just 90 degrees north. The South Pole would be negative 90 degrees or just 90 degrees south. And then there's also longitude, which is the east-west coordinate. Now, there's no good place to define 0 degrees longitude. It's completely arbitrary. But we have, by convention, chosen London, or actually the Greenwich Observatory, as the reference point, as for 0 degrees longitude. So I can actually turn on the latitude and longitude system here in Google Earth. If I go up here to View Grid, right there you can see the latitude and longitude for everything on the Earth. So 0 degrees is the prime meridian, which goes through Greenwich Observatory. An observatory. There must be an astronomical reason for choosing that point for 0 degrees longitude. There is. Maybe I'll talk about that in a separate video about timekeeping and celestial navigation. But that's just what we've chosen by convention. And then 0 degrees latitude is the Earth's equator, which is, of course, midway between the North and the South Pole. So in a sense, the latitude and longitude grid is defined by the rotation of the Earth, because the Earth rotates on its axis. That defines the North and South Pole. And then midway between those two is the equator. And then, as I said, we arbitrarily choose Greenwich Observatory for 0 degrees longitude. Now, if we project this grid up into the sky, onto the celestial sphere, we have celestial latitude and longitude. So if I go back to one of these simulations, this is one for terrestrial latitude and longitude, and probably most of you are already familiar with this. You can go a certain number of degrees to the south, all the way down to 90 degrees south. 0 is the equator, all the way up to 90 degrees north. 45 degrees, of course, is midway, and there's actually, if I remember correctly, there's a town in Oregon called Half Oregon because it's right at 45 degrees north, so it's halfway between the equator and the North Pole. So that is just latitude and longitude. By the way, the units here, or the base, you can either have a decimal with tenths of a degree and hundredths of a degree and so forth, or often we use this base 60 sexagesimal system where you have minutes of arc, you could have seconds of arc, and just like with timekeeping, there are 60 arc minutes in a degree and 60 arc seconds in an arc minute. That's just another way of recording angles. Astronomers tend to use both. You kind of run into them kind of equally, although when you write a computer program to process angles, you're going to want to use decimal angles, not base 60 sexagesimal angles with arc minutes and arc seconds. So kind of a pain, you have to convert to decimal. Anyway, as I was saying, project these coordinates up into the sky, and you have the celestial sphere. This is an imaginary sphere that's concentric with the Earth. Project the Earth's North Pole up so that it intersects that sphere. You've got the North Celestial Pole. And then down at the bottom, take the Earth's South Pole, project it up into space. You've got the South Celestial Pole. Take the Earth's equator, project it up into space. You've got the celestial equator. Now, this particular module or a simulator allows us to look at the celestial sphere versus where the equator is horizontal versus the local horizon system where the horizon is horizontal, right? So here we're keeping 0 altitude sort of horizontal as we kind of scroll around the celestial sphere. And then if I switch back to the celestial system, now we've got the equator horizontal. And this is a nice way to show that the celestial system does not care about your latitude and longitude, right? So as I move around, as I change my latitude, that white circle on the Earth, the North Celestial Pole is fixed, the South Celestial Pole is fixed, the celestial equator is fixed, and this line here is supposed to represent the celestial prime meridian. This is the point of 0 celestial longitude. I'll come back to that in a second. Also being shown on here is the horizon circle, which is that circle right there, and that must be the east-west line. So that would be a line going across the sky from east to west. Let's switch back here so you can see that. Yeah, so that's a line that would go from east through the zenith and then into the western horizon. That doesn't have a name in classical astronomy. This, though, allows you to see how the position of the North Pole and the South Pole change with your latitude, right? So as I walk around the curvature of the Earth, if I go to the North Pole, then the North Celestial Pole is directly over my head. If I go to the equator, then the celestial equator is directly over my head. And if I go into the southern hemisphere, I can't see the North Celestial Pole anymore, but I can see the South Celestial Pole. And if I go all the way to the South Pole, latitude negative 90 degrees, there it would be directly over my head right there. I would be at the South Pole at the Scott Amundsen station in Antarctica if I were at that point. Kind of at mid-northern latitude, if I kind of go to the typical latitude of New Haven, maybe like 40 degrees or so, right about there. There you can see where the celestial equator is coming out of the east horizon. You can see where the North Celestial Pole is right there. It turns out that the angle between the North Celestial Pole and the North Horizon is equal to your latitude. So if I were to make this closer to 0, you can see there it's a small angle. If I make this bigger, if I go further around the curvature of the Earth, you can see it's quite steep, and so the North Celestial Pole is high above the North Horizon. And if I go into the southern hemisphere, it goes below the horizon, and so its altitude would be negative, and I would have a southern latitude, a negative latitude, if you like. I can actually switch back to, there we go. So see, my point on the Earth is a little bit south of the equator here. If I go down here, there you see I'm quite far south of the equator. If I switch back to the horizon mode, there's my horizon, and then it flips over so the zenith is at the top. So two different ways of showing the celestial sphere with the zenith, your local zenith at the top, that's going to depend on your latitude, or with the North Celestial Pole at the top, like so. Generally, when you're looking at celestial latitude and longitude, it makes more sense to orient the celestial sphere like this. And if you're talking about local coordinates of altitude and azimuth, it makes more sense to orient it like this, because then 0 altitude is around the edge of the green ring, around the edge of the green circle, and the zenith is overhead, the nadir is beneath your feet, and so forth. Now, it's actually very convenient that there is a star that's very close to the North Celestial Pole. So there's a star called Polaris, the North Star. Not the brightest star in the sky, but bright enough. It's in the top 100 or so brightest stars. It's bright enough you can see it pretty much anywhere. So if you can find Polaris, that's going to tell you which way is due north. So that's a useful navigation tip. Now, if we're going to have a celestial analogy to latitude and longitude on the surface of the Earth, but projected up onto that celestial sphere, we need reference planes. So the celestial latitude, it makes sense to use the celestial equator as the reference plane. And of course, that's what we do in astronomy. So celestial latitude, also known as declination. So get used to this. This is the term I'm going to use from now on, declination. It's 0 on the celestial equator. An object like a star or a planet or the sun is going to have declination 0 when it's on the celestial equator. And it's going to have declination 45 degrees if it's halfway to the North Pole, and it's going to have declination 90 degrees if it's right on the North Celestial Pole. Now, this is not altitude, this is not azimuth. As the Earth turns underneath, the stars do not care about the rotation of the Earth, do not care about your latitude and longitude. Stars essentially have a fixed declination on the sky as the Earth is turning underneath you here. Now, for celestial longitude, again, we need a reference point. How about the point directly above Greenwich Observatory? That'll be 0 degrees terrestrial longitude and 0 degrees celestial longitude. Well, the problem with that is that the Earth turns. So if the Earth were turning 360 degrees in 24 hours, that point above Greenwich would spin around the celestial sphere. And a star, we want to have a star that has a fixed celestial latitude and longitude no matter how the Earth is turning, no matter what time it is on the Earth, or year, date in the year, and so forth. So we need a point that's fixed on the celestial sphere. So we arbitrarily choose the point where the sun is on the spring equinox. So over the course of a year, the sun moves around the celestial sphere along the ecliptic. And I have another video on that, motion of the sun and the moon. So the sun's moving along the ecliptic to the east. Once a year, it crosses the celestial equator going from south to north. We call it the spring equinox. 6 months later, it crosses the equator going from north to south. So that's the fall equinox. That's when it has a declination of 0. I could drag my star over there to, let's say that star is representing the sun. Now, that is by definition where the sun is on the spring equinox, 0 degrees celestial longitude. Now, for historical reasons, again, we don't record celestial longitude in degrees. We do it in hours of time. So we take 360 degrees around the celestial equator, and we divide it up into 24 hours. Because, of course, the Earth turns 360 degrees in 24 hours. So a star at a certain right ascension, a certain celestial longitude, is going to be overhead at a certain time. 24 hours later, the Earth turns 360 degrees. It'll be overhead once again. So there is a way in which right ascension is connected to timekeeping. So you just have to remember that 1 hour of time is equal to 15 degrees of angle. So there you see we moved 1 hour around to the east. Let's move 2 hours around to the east. Also, there we go, 2 hours. So 30 degrees. So 2 hours would be 30 degrees around to the east. We go 4 hours around. Let's actually go 6 hours around. Now 6 is 1/4 of 24. So that's actually 90 degrees around from the reference point for celestial longitude. So that is celestial latitude and longitude. Has nothing to do with your latitude, has nothing to do with time or anything on the surface of the Earth. It's what we think of as a fixed grid attached to the celestial sphere. Let me label some of these important reference circles. So there's the celestial equator directly above the Earth's equator, north and south celestial poles. So there's the North Pole and the South Pole on the Earth. There's the North Celestial Pole and the South Celestial Pole. I'll just label the ones on the celestial sphere, not on the Earth. The Earth is turning to the east. Right ascension, it turns out, also increases to the east, just like longitude on the surface of the Earth, by the way. So if I increase my right ascension by dragging that slider to the right, that star's right ascension increases. So that's pretty straightforward. If you were to, drag this sample star anywhere on the celestial sphere, if you were to not show, if you were to sort of hide the right ascension declination somehow, you ought to be able to just sort of estimate its celestial latitude and longitude, just as you should be able to estimate the celestial latitude and longitude of a city or a place on the Earth just by looking at where it is relative to Greenwich Observatory and the prime meridian and the Earth's equator, which is 0 latitude. Now, what can get tricky, what can be hard to understand is then when you think about where this star should be in your local coordinate system as the Earth is turning and as you're looking at different latitudes, and that's a little bit more complicated. Now, this module right here, which is the Rotating Sky Explorer, also on the University of Nebraska website, allows us to see both the celestial coordinate system with the North Celestial Pole at the top here and the local system with the zenith at the top at the same time. So this is kind of convenient for trying to figure out how the system works. So here I am at some random latitude. Let's actually plop down close to New Haven, although I don't care if I'm exactly at New Haven. So there you see where I am on the globe of the Earth. And if I were to put a star, add star randomly. Okay, there it is right there. This would actually be an interesting test. Okay, what's the celestial latitude and longitude of that star? It's in the southern hemisphere of the celestial sphere, so it's a negative declination. I'd say maybe -10, -7. It is to the east of the celestial prime meridian. That line looks like that's a 90 degree or 6 hour line. So if we just look from above here, that would be 0 right ascension, 6 hours right ascension, 12 hours right ascension, 18 hours right ascension, and then back to 0 right there. So it looks like that star is like an hour shy of 6 hours. So I'm going to say declination -7, and right ascension 5 hours. All right. Okay, if I click on it, it gives me the data. Oh, -6.6 degrees declination, right ascension 5.2 hours, right ascension relative to the celestial prime meridian. Okay, where is that in my local sky? All right, well, here's the celestial equator in a local sky. There's the North Celestial Pole in the local sky. I can't see the South Celestial Pole, of course, because the Earth is in the way if I'm at latitude 36 degrees. So there's the star down there. Now, if I let time pass, let's let the sky rotate. As the Earth rotates. So as the Earth rotates, there it goes. Now, at some point, the star is above my horizon. So there you see, there it is right there. So in terms of its azimuth and altitude, there you see its azimuth is 180.9. It's pretty close to the local meridian. And its altitude is 47.1. So let's let time pass. Right, there's the Earth turning. Its right ascension and declination are not changing. Right, those are essentially fixed. But its altitude and azimuth are changing. So now I can't see it below the horizon. There are stars in the southern sky that you might not be able to see at this latitude just because the Earth is in the way. So if I actually drag this guy down to, there's negative 53.9 degrees declination. Now that guy, can he get above the southern horizon? He's making a circle around the South Celestial Pole right there. Here you see his altitude is -60. Here it is coming up, getting close to the horizon. Let's see if it clears the horizon. Just barely doesn't clear the horizon. It got to -0.2 or something like that degrees altitude. So that's a star. That's a part of the celestial sphere I would never be able to see from that altitude. There are stars down there like the Southern Cross, all the constellations of the southern hemisphere that I can't see from that latitude. So this is kind of a problem in observational astronomy, is you want to know an object with a particular right ascension and declination, how high is it going to get above my horizon? Well, it turns out there's a simple relationship between a star's declination and your latitude and how high it will get above the horizon. So for example, if I put this star at 0 degrees declination right there, it's going to be on the celestial equator. And it turns out that the celestial equator crosses the local meridian, that point right there. It crosses at a point which is equal to an altitude of 90 degrees minus your latitude. So I said that the altitude of the North Pole is plus 90 degrees. There it is right there, or plus 90 degrees. It's equal to your latitude, what I meant to say. So this is this is your latitude right here. From the North Pole to the equator has to be 90 degrees. That's always the case. Pole to equator has to be 90 degrees. So then from north horizon to south horizon has to be 180 degrees. So we've got your latitude, we've got 90 degrees. We've got this angle from the celestial equator to the horizon. That has to be 90 degrees minus your latitude. So if we let time pass again, get that star close to, let's see, spin it around. Actually, we'll just drag it to there, so cheat a little bit. So there it is, close to the local meridian, and its altitude is 53.1 degrees. So that has to be equal to 90 degrees minus my latitude. Yeah, that's very close. Not exactly, but that's very close. I'm not exactly on it, but that's very close to 90 degrees minus my latitude. Now, if the star had a negative declination, let me drag it down here by about 10 degrees or so. Right, put it right about there. It's going to be 10 degrees south of the equator in my local sky. If I take it 10 degrees north of the celestial equator, now it's about 10 degrees, drag it around a little bit. Now it's about 10 degrees north of my equator in my local sky. So it's going to appear 10 degrees higher in the sky when it transits. If it's 10 degrees north, it's going to be 10 degrees lower in the sky, to an altitude 10 degrees less, if its declination is negative 10 degrees. So that's the connection between declination and then altitude in your local sky and your local latitude. All right, that's pretty complicated. So I recommend that you kind of play around with this in your spare time, drop a few stars on the celestial sphere and make sure you understand the relationship about how their celestial latitude and longitude, their right ascension and declination, affects how they appear to move in your local sky, right? So we can actually run this here. And so you can see that star right there, which is at fairly high declination, 57.5 degrees, is in my northern sky. And there you can see its altitude and azimuth changing as it goes around the North Celestial Pole as the Earth is rotating. That area that you can never see at your latitude, I can highlight that right here. There it is right there. At that latitude, I'll never be able to see the stars on that part of the celestial sphere. Conversely, there's a part of the celestial sphere in the north where the stars never set. So that's called circumpolar. Those stars are circumpolar up there. And I could figure out where that is based on my latitude, right? It's going to be a declination of 90 minus my latitude. So that those declinations are always going to be circumpolar. Now, let's see what this looks like in the Planetarium Simulator. So here I am actually in New Haven, and I want to see that right ascension and declination, the celestial latitude and longitude coordinates. So I'm going to go to the settings again, sky and viewing options. I'm going to turn on the equator. Let's see, I'll turn on the equatorial grid for now. I'm going to turn it off again in a second. So there is the celestial sphere with right ascension coordinates and declination coordinates indicated. So the equator has declination 0. Here's, let's see, what's that, plus 10? Yeah, there it is marked there. Plus 10, plus 20, plus 30, and so forth all the way up. Minus 10, minus 20, minus 30, and so forth all the way down. And then there's a region that I wouldn't be able to see from New Haven. Now, this is a simulation of the sky, so if I want to turn off the ground, I have that option. All I have to do is go down here and hit the G key or click on that icon, and the ground disappears. Now I can see the South Celestial Pole right there and all of these stars down here that I would not be able to see. I'm going to turn the ground back on for now. Now, I selected Vega. Where is Vega in the sky right now? There it is over there. Now, Vega also has a particular right ascension and declination. So let's turn that back on in the information box here. So we'll say right ascension declination, like so. So now you can see there's its right ascension declination for the year 2000, 18 hours, 36 minutes, and some seconds. 38 degrees, 47 arc minutes, and some seconds. So that tells you where it is relative to the equator and relative to that arbitrary point where the sun is on the spring equinox. So if I let time pass again, let's speed time up. This is a very important point. The altitude and azimuth of the star are changing. The altitude's going down, the azimuth is increasing. But the right ascension and declination are not changing because the grid is rotating and carrying the stars with them. Now, that's not literally 100% true. The stars do move around relative to each other, just because we're all orbiting around the center of the Milky Way. I'm going to turn off the atmosphere so we can see the stars here even when the sun's up. The stars are, of course, moving through space as we all orbit around the center of the Milky Way, so their positions relative to each other will change. That's a motion called proper motion. It's very, very slow. So most of the time you don't have to worry about it unless you're worried about the positions of the stars over long periods of time. Another effect is that the coordinate grid does move due to an effect called precession of the equinoxes, and I have another video about that as well. The precession effect means that you need to know the date for the coordinates. So right ascension declination for 2000, those are going to be fixed. But if I wanted to know right ascension declination for this year or this moment, this will change very, very slowly because the coordinate grid does actually move around over time. Okay, so I can look to the north, and I can see the North Celestial Pole right there, and I can see the star Polaris right there. It's not exactly on the North Celestial Pole, but it's close enough to be useful for navigation. I can see the celestial equator coming out of the east horizon right there. It crosses the local meridian right there at an altitude equal to 90 degrees minus my latitude. And then it goes down here into the western horizon over there. All right, now any asteroid, planet, star, whatever, galaxy, quasar is going to have a particular right ascension and declination, and those are the coordinates you're going to use to point your telescope. So you calibrate your telescope with some known star or known object, and then you can move the telescope a certain angle, north, south, east, west, and find that object. Okay, one last thing I want to say about these two coordinate systems, and especially using Stellarium. Stellarium is kind of designed for amateur astronomers who are planning observations, and by default it's in this local coordinate system, coordinate mode, where the horizon stays horizontal, right? And I look straight overhead to see the zenith. A mode that's useful when you're looking at the celestial sphere is the so-called equatorial mode, or they call it equatorial mount mode. So I would hit Command M to switch that with the keyboard, but I can also just click on that little telescope icon right there. And it changes the orientation of the sky so that instead of having a horizon that's horizontal, you see it's tilted now, Stellarium is keeping the celestial equator horizontal, like so. So now when I look overhead, I see the North Celestial Pole. If I look beneath my feet, well, directly beneath my feet would be the South Celestial Pole. I have the ground in the way, so this might be a good time to turn off the ground. There we go. So this is now as if maybe the Earth didn't exist or the Earth were transparent. I look beneath my feet and there's the South Celestial Pole. I look horizontally and there's the celestial equator. East is to the left, west is to the right, north is up, south is down. And then I look overhead and there's the North Celestial Pole up there. All right. I just mentioned that thing about east to the left, west to the right, and so forth. That's kind of a useful thing to know when you're looking at star maps. For example, here, if we look at the constellation of Orion, and I'm just going to zoom in on it a little bit. There you see the meridian going by. I'll just hide that for now. So there's the constellation of Orion. If I look at the star Rigel down here, the lower right foot, you can see, okay, it has a... it's hard to see the coordinates. Let me turn off the grid for a second so we can see those coordinates a little bit better. I have to turn it off. I have to turn it off over here. I have to turn it off right there. Okay. So you can see those coordinates. So it's at 5 hours and 14 minutes, and then negative 8 degrees declination, 12 arc minutes. So it's south of the celestial equator. Versus the star over here, Betelgeuse. So Betelgeuse, if north is up, Betelgeuse is kind of to the left of Rigel on the celestial sphere, and it's up. It's north. It's sort of closer to the North Celestial Pole. You can kind of figure out these north, south, east, west directions by looking at the coordinates. So Rigel here has right ascension, I just said 5 hours, 14 minutes. Declination, negative 8 degrees, 12 minutes. Betelgeuse is north of the celestial equator, so it's got a declination of plus 7 degrees, 24 arc minutes, and a right ascension of 5 hours, 55 minutes. Its right ascension is bigger. So it is to the east on the celestial sphere of Rigel. Its declination is more positive, so it is north of Rigel on the celestial sphere. So that's kind of how astronomers use directions. Notice that north is up, south is down, but east is to the left and west is to the right. That's kind of the opposite of how you normally look at a map, right? And of course, the reason why is because when you look at a map, you're looking at the outside of the sphere of the Earth. When you look at the celestial sphere, you're looking at the inside of the sphere. So even though east and west are in the same directions on the spheres themselves, if you look at the inside of the sphere, east and west end up being reversed. It's something that astronomers are often confused about. All right, so that's a lot of information about celestial coordinates. I'm going to review this in a couple of different ways, but these are the most important basic things. So right ascension declination, celestial longitude and latitude, cataloged for all the objects in the sky. And then your local system then is altitude and azimuth, just the height above the horizon and the angle relative to north. And we use both of these angles, we use both of these coordinate systems to measure positions of objects in the sky in observational astronomy.